Hello and welcome back to Anton Math. Now in the last video we introduced vectors, just a very basic idea of what a vector is and some of the vector operations. And we're going to generalize that idea in this video to what we call matrices. Now I know you've all heard of matrices or you've heard of what a matrix is, and I don't mean the movie. But matrices are really just a generalization of vectors. Instead of a ordered set, we're going to look at an ordered array. So matrices, just as we can write linear equations as a vector equation, and it looks like I've left out my little dot here, but it's easy to see that we can write the equation 2x plus y as the vector dot product 2, 1 dot xy. All right, we can see that without much trouble from the dot product we learned last video. Now we can do the same thing with a system of linear equations. We can write it as a set of vector equations. So this becomes the set of vector equations 2, 1 dot xy, and then down here I'm going to have 3 and negative 2 dot xy, and this set of equations has a set of solutions on the right hand side of the equations there. We have 3, 1. Now we can kind of undo this dot product, and really this becomes what we call a matrix. This is going to be a 2 by 2 matrix, 2, 1, 3, negative 2. And the rest of the equation kind of looks like this. We're going to have this column vector xy here that we're multiplying by, and we're going to get our solution vector 3, 1. Now we haven't introduced vector or matrix multiplication, so this won't make sense just yet, but really this is what I'm talking about right here. While all of these are matrices, this 2 by 2 is kind of what I want to talk about in this video. We call these multidimensional matrices, or multidimensional kind of vectors, a matrix. Instead of just a line of values, I'm going to have an array of values that goes in two directions. Now, for example, let's say I have this matrix, and I'm going to call it A. I'm going to do a little 2 by 3 down here. We'll talk about that in a second. And I don't know, I'll just throw some random numbers in here. It doesn't really matter for this example. So this would be an example of a matrix. Now the I wrote 2 by 3, but I meant to write 3 by 4. Let me clean this up a little bit. Okay, 3 by 4. I made a 3 by 4 matrix and I wrote 2 by 3. Now what this 3 by 4 right here means is that we're talking about a matrix that has 3 rows and 4 columns. Now notice that each row is just a 1 by 4 vector, right? I have this row right here, for example, is going to be a vector of dimension 4. Each column is also a vector. For example, this first column, this is a vector of dimension 3. And the element in the ith row and jth column, we usually denote A subscript ij, and we'll typically write the matrix A equals, down here, the matrix A equals this little parentheses aij. So for example, this 1 right here, this is A1, 1. This 4 over here, this is A2, 3, right? The second row, third column. Now, writing a matrix in this way, A equals Aij with parentheses about it, this is really the most convenient when we're given a closed formula for Aij. So for example, let's say we want to know what the 3 by 3 matrix is, where A equals Aij, and Aij equals I plus j. Well, then my matrix A, it's a 3 by 3 matrix. Aij equals I plus j. So this first entry here we just saw was A1, 1. So this entry is going to be 2 because my I is 1 and my j is 1. Similarly, these two entries, this is A1, 2, this is A2, 1. So I plus j is 3. And if I look at A3, 1, A2, 2, or A1, 3, those all add up to 4. Over here we'll get 5 for A23 and A32, and A33 gives me 6. Right, so if we're given a closed formula for Aij, like this one we were here, it's really easy to generate a matrix based on that formula. Now, that's the basic introduction, so let's talk a little bit about matrix operations. Now, as matrices are kind of generalizations of vectors, the vector addition and the vector scalar multiplication that we talked about in the last video carries over to matrices as well. Matrix addition is going to be component-wise, and scalar multiplication just multiplies through that scalar to each entry in the matrix. Let's do an example here. So I'm not being very explicit with these operations. Let's make sure we all understand what's going on, generalizing this from vectors. So let's say I have this, that's a 1. Let's say I have these couple of matrices. Now let's make C a little bit different than these two. Let's make C a 2 by 3 matrix. So for example, we could have something like A plus B. And here addition is just going to be entry-wise, component-wise, right? So I'm going to add the entries in the same component Aij. So A11 plus B11, let's call it, it's going to be -1 here for my A plus B11. Here I look at 3 plus 0 is 3, -1 plus 1 is 0, and 2 plus 4 is 6. So we get another 2 by 2 matrix. We can kind of combine addition with scalar multiplication like we did with vectors. If I look at 2a minus 3b, well, what I'm doing here is I'm going to multiply all of the entries in a by 2. I'm going to multiply all of the entries in b by -3, and then perform matrix addition. So here I'm going to have 2 plus 6 gives me an 8. Here 6 plus 0 gives me a 6. Here I'll have -2, and here I'll have -3. I'll give me -5 right here. And here I'll have 4, and here I'll have -12, so I'm going to have a -8 down here in the bottom right of my matrix. Now if I look at something like -c, remember that's just scalar multiplication through c by a -1. So all of the entries are going to change their sign. Right? This is just to say when we multiply by a scalar, we multiply through to every entry, not just an entry in the first row or something like that. And if I wanted to talk about 3a plus c, well, let's take a look at it. I can find 3. I'm just going to take a, I'm going to multiply through everything by 3. But what would 3a plus c look like? C is a 2 by 3 matrix, and a is a 2 by 2 matrix. So just like with vectors, this does not exist. Right? To do matrix addition, we need to have both matrices have the same dimension, both the same number of rows and the same number of columns. So matrix addition is only going to be defined with matrices of the same dimension. All right, now that's the basic operations. I'm going to go ahead and just do a different video for the matrix product because it's a little bit more in depth, so we'll see you over there.